Let's understand the process of how to calculate the number of divisors or factors of any given number. So the process obviously starts by finding the prime factorization of a number. So for example, if the number is 200, the prime factorization of this number can be written as 200, 250, and 225, which is 5 times 5. So the prime factorization of 200 is 2 raised to 3 into 5 raised to 2. So any number on any divisor of 200 is basically a number which can be factored out from the prime factorization. So for example, 2. I can factor out 2 from the prime factorization of 200. So if I factor out 2, the remaining thing is 2 squared into 5 squared. If I factor out 5, the remaining thing is 2 raised to 3 into 5 raised to 1, which basically tells me that 2 and 5 are both factors of 200. Similarly, there can be other factors found. So one of the examples I can take is factoring out 2 and 5 together. So if I factor out 2 and 5 together, what's remaining is 2 squared into 5 raised to 1. And 2 into 5 is basically 10. So I can say that 10 is also a factor of 200. One more example. I can even factor out 8, which is 2 raised to 3. So if I factor out 2 raised to 3, the remaining thing is 5 squared. That means 2 raised to 3, 8 is a factor of 200. So this process basically indicates that all the factors of 200 have a certain form. So if I want to write the general form of the factors of 200, I can say the factors of 200 are of the form 2 raised to a into 5 raised to b, where a belongs to the integer set of 0, 1, 2, 3, 0, 1, 2, and 3, and b belongs to the integer set of 0, 1, 2, 0, 1, and 2. So the possibilities for the power of 2 here is either 0, 1, 2, or 3, and the possibilities for power of 5 is 0, 1, or 2. That means the possibilities for the power of a is 4, and the possibilities or the possible values for the power of b is 3. So there are in total 4 into 3, which is 12 combinations possible. 12 combinations possible means there are total 12 divisors of 12 factors of 200, and 12 factors including 1 and 200 itself. Because 2 raised to 0 and 5 raised to 0, which is 1, is also a part of this counting process. Similarly, 2 raised to 3 into 5 raised to 2 is also a part of this counting process, which is 200. So the number 200 has 12 positive divisors. Let's investigate how to find the number of factors for a certain type of numbers. So for example, find the number of factors of 98. So for 98, number of factors for 98. So let's start. Firstly, we start by writing the prime factorization of 98. So 98 is divisible by 2, so which is 2 4s are 2 9s are 49, and 49 is 7 squared. So the prime factorization of 98 can be written as 2 raised to 1 into 7 raised to 2. So now let's start by the process of counting. So this is 2 raised to 1 here. That means the possibilities for here is either 0 or 1, and the possibilities for the power of 7 is either 0, 1, or 2. So that means 2 possibilities into 3 possibilities, which is 2 into 3, 6. So there are total 6 factors for 98, including 1 in itself. Moving on to the next question, they're asking how many of the positive divisors of 168 are even. So we'll start by writing the prime factorization of 168, so which becomes 2 84s are, 2 42s are, 2 21s are, and then 3 7 and 7 7. So that means the prime factorization of 168 is 2 raised to 3 into 3 raised to 1 into 7 raised to 1. But they're not asking us here all the divisors of 168. They're asking the ones specifically even. Answering this question requires the understanding of the general form of even numbers. So we know that if I have an even number, any even number can be written in the form of 2k, where k belongs to positive integers, if we exclude 0. So any even number can be written in the form of 2k. So what I'll do is I'll factor out 2 from the prime factorization of 168. So if I factor out 2, I'll get 2 raised to 2 into 3 raised to 1 into 7 raised to 1. To count the number of even divisors of 168, basically what we have to do is I'll just write some examples firstly. Some examples of even factors of 168. One of the possibilities could be to consider 2 raised to, instead of 2 raised to 2, 2 raised to 1, and 3 raised to 1 into 7 raised to 1. So this is an even factor of 168. Since it's 2k form. Another possibility is 2 raised to 0 into 3 raised to 0 into 7 raised to 1. So this also counts as an even factor of 168. So can I say that the number of even factors of 168 is the same as the number of divisors of the thing inside, which is 2 raised to 2 into 3 raised to 1 into 7 raised to 1. So that means the number of even divisors of 168 can be found by just finding the number of divisors of the term inside after factoring out 2, which is 2 raised to 2 into 3 raised to 1 into 7 raised to 1. And that process is quite easy because I know this is 2 raised to 2 here. That means 3 possibilities, 3 raised to 1 here, which has 2 possibilities, and 7 raised to 1, which has 2 possibilities. So the multiplication gives me 12. So there are a total of 12 even divisors of 168. Next, we will investigate perfect squares. So perfect squares are numbers which can be written as a square of any integer. So for example, 2 squared is 4, 3 squared is 9, 5 squared 25, 6 squared 36, 10 squared 100, and 12 squared 144. Let's try to understand the prime factorization of each perfect square. So for 4, the prime factorization is 2 squared. For 9, it's 3 squared. For 36, it's 6 squared, which is 2 into 3 squared, which is 2 squared into 3 squared. For 100, it's 2 into 5 squared, which is 2 squared into 5 squared. And for 12 squared, it's 4 into 3 squared, which is 4 squared into 3 squared, which further gives me 2 raised to 4 into 3 raised to 2. So one thing to observe here is that the powers of the primes in each prime factorization is even for perfect squares, which is a visible result here. So let's try to prove the general statement here. So suppose I consider an integer I whose prime factorization looks as follows: p1 raised to a1, p2 raised to a2, or p3 raised to a3. I'll just consider 3 primes here, where p1, p2, p3 are primes. So for I squared, or basically squaring this integer, the prime factorization can be obtained using the laws of exponents. So if I do this raised to 2, I get p1 raised to 2a1, p2 raised to 2a2, and p3 raised to 2a3. Since 2a1 is 2k form, which is the form of even numbers, I can say this is 2a1 is even, 2a2 is even, and 2a3 is even, which is a simple proof that for a perfect square, the powers are even. One more result which follows from this is the number of divisors. Number of divisors of perfect squares. So considering the general case, which is I squared. So I squared is p1 raised to 2a1, p2 raised to 2a2, and p3 raised to 2a3. So counting the number of divisors basically says that, okay, if this is 2a1, the total number of possibilities in this place will be 2a1 plus 1. The total number of possibilities for the second exponent is 2a2 plus 1, and the total number of possibilities for the third exponent is 2a3 plus 1. So it's visible that 2a1 plus 1 is an odd number, 2a2 plus 1 is an odd number, and 2a3 plus 1 is an odd number. So if I multiply odd numbers, odd into odd into odd, will result in me getting an odd number. That means the number of divisors of perfect squares is always odd. This is an important result to remember. To the next question, how many divisors of 5400 are not multiples of any perfect square greater than 1? So we'll start with the first step, which is prime factorization. So for 5400, it'll be 2 2s are 2700, which is 2 1s are 2 3s are 2 5s are 1350. Then divisible by 3, which is 3 4s are 12, 3 5s are 15, 450. Which is again divisible by 3, which is 3 1s are 3 5s are 150s. 3 times 50, and then 5 times 10, 5 times 2, and 2 times 1. So the prime factorization is 2 raised to 3, 3 raised to 3, and 5 raised to 2. So the question is asking how many divisors of 5400 or how many factors of 5400 are not multiples of any perfect square greater than 1. So let's try to understand the cases wherein the divisors are multiples of perfect squares greater than 1. So one of the examples I can think of is 3 squared. So 3 squared is the perfect square. So then any multiple of 3 squared can be all the possibilities for 2 raised to 3. So it can be 2 raised to 2 into 3 raised to 2 into 5 raised to 1. So this is basically a multiple of a perfect square. Having 2 raised to 2 here and 3 raised to 1 here and 5 raised to 1 here is also a multiple of perfect square. Also having 2 cubed, 2 raised to 3 and 3 raised to 3 and 5 raised to 1 is also a multiple of a perfect square, because here we can just factor out either 2 squared or 3 squared, which basically implies that this number is a multiple of a perfect square. So in any case wherein the power of the prime is 2 or more will be a multiple of a perfect square. That means if I consider the number 2 raised to 1 into 3 raised to 1 into 5 raised to 1, here no perfect square can be factored out, because to be a perfect square the number has to be at least 2. The power or the exponent has to be at least to be even, and the smallest even number is 2. So this number is not a multiple of a perfect square greater than 1. Also having 2 raised to 0 here, 3 raised to 1 here, and 5 raised to 0 here is also not a multiple of a perfect square. Having 2 raised to 1, 3 raised to 0, and 5 raised to 0 is also not a multiple of a perfect square. So what I can do is I can systematically count those numbers which are not multiples of a perfect square. That means for the first power, the options are 0 and 1. For the second power, the options are 0 and 1. And similarly, for the third power, the options are 0 and 1. So that means 2 into 2 into 2, which is in total of 8 numbers. So 8 divisors of 5400 are not multiples of any perfect squares greater than 1. So the next AOPS question is, if n is a perfect cube of a natural number and n has 28 positive divisors, 2 of which are prime, how many positive divisors does the cube root of n have? Okay, so they're saying n is a perfect cube. So perfect cube. So for example, if supposedly my number is p1 raised to 3 into p2 raised to 6, the question is this the perfect cube? So yes, it is a perfect cube, because this number can be written in the form of p1 into p2 raised to 2, the whole thing raised to 3. So any number which can be written as an integer raised to 3 is a perfect cube number. So one thing is visible here, that if a number is a perfect cube, the prime factorization of the number can be written in the form p1 raised to, and in the power I can have 0, 3, 6, 9, which are basically all multiples of 3. So, and similarly p2 raised to either 0, 3, 6, 9. So if in the power I have multiples of 3, including 0, I can say that number is a perfect cubed. Okay, so keeping this fact in mind, we'll just read the question ahead. They're saying an n has 28 positive divisors. So let's try to understand which numbers multiplied give us 28. So 28 I can get as 4 into 7. 28 I can also get as 2 into 14 and 1 into 28. Yeah, so I think these are the only possibilities which give me 28. 4 into 7, 2 into 14, and 1 into 28. So that means for a number to have 28 positive divisors, and especially considering the first case, in the first case for a number to have 28 positive divisors and is a combination of 4 into 7, that means the prime factorization has to look something like this: p1 raised to 3 and p2 raised to 6. Because if the prime factorization looks like this, I can count the divisors as 3 plus 1, 4, and 6 plus 1, 7, 4 into 7, 28. For being a prime of this form, 2 into 14, a number of this form, 2 into 14, what I can do is I can say the prime factorization of such a number could be p1 raised to 1 into p2 raised to 13. Because in this case, then I'll add 1 here, so which will give me 2, add 1 here will give me 14, so which will be 28. And for the last case, I need to have p1 raised to 0, which basically is the same as not considering the prime. So it's basically the prime factorization has just one prime in it raised to 27. So in this case, the number of divisors are, again, I'll have 27 plus 1, which is 28 positive divisors. So these are all the possibilities of having 28 positive divisors. But what they're saying is 2 of which are prime. That means the prime factorization needs to have 2 prime numbers. So which sort of discards the last case of the number being p1 raised to 27. So I'm left with 2 possibilities. Either it's p1 raised to 3, p2 raised to 6, or p1 raised to 1 and p2 raised to 13. One more thing to consider is that n is a perfect cube. If n is a perfect cube, it can't be of the form p1 raised to 1 and p2 raised to 13, which discards the second case as well. So what I'm left with is a prime or a number of the form p1 raised to 3 and p2 raised to 6. So my n is of the form p1 raised to 3 and p2 raised to 6. Asking how many positive divisors does the cube root of n have? So if I take the cube root of n, that is the same as saying p1 raised to 3, p2 raised to 6 cube root, which gives me p1 raised to 1 and p2 raised to 2. So now to count the number of positive divisors of the cube root, I'll just have to add 1 here and add 1 here. So it will give me 2 into 3, which is 6. The cube root of n has 6 positive divisors. The next question is how many of the positive divisors of 960 have 6 positive divisors themselves? So 960, firstly writing the prime factorization, it's 2 into 480, 240, 120, 60, 30, and then 15, and then 3 5s are, and 5 1s are. Yeah, so the prime factorization of 960 is 2 raised to 6 times 3 raised to 1 times 5 raised to 1. So I have to find the positive divisors of 960 which have 6 positive divisors themselves. So firstly, let's try to understand what numbers multiplied give you 6. So the first possibility is 2 into 3, the pair of 2 and 3, and the second possibility is 1 into 6. So to have 6 positive divisors, considering the first case of 2 into 3, the divisors have to be of the form p1 raised to 1 into p2 raised to 2. Because these divisors of this form will actually have 2 into 3, which is 6 positive divisors themselves. 1 into 6 form numbers have just 1 prime in them, which is of the form p1 raised to 5. So actually, we'll approach this question by understanding how many possibilities are there for the second case. Because the prime factorization here, for 2, the highest power is 6, while for 3 and 5, the highest power is 1. So the only divisor or factor of 960 of the form p1 raised to 5 is 2 raised to 5, which is 32. So 32 is a positive divisor of 960, which itself has 6 positive divisors. So we are done with the second case here. Now let's try to understand what numbers of the form, or what divisors of the form p1 raised to 1 into p2 raised to 2 are possible. So looking at the prime factorization, 3 raised to 2 is not a possibility because the highest power is 1. And similarly, 5 raised to 2 is also not a possibility. The only possibilities are 3 raised to 1 into 2 raised to 2. 5 raised to 1 into 2 raised to 2. And yeah, there's no other possibility because 3 and 5 can only be raised to 1. So the first number is 3 times 4, which is 12. And the second number is 5 times 4, which is 20. So 12 and 20 are also divisors of 960, which have 6 positive divisors themselves. So the answer for this question is 12, 20, and 32.